Hey, hello Physics 110 students. Let me go ahead and make a video solution of exam number 2. And let's try to do two goals here. The first one is use this as an educational opportunity to go through and see what you've done right and wrong. And of course, then if you did it wrong, learn from those mistakes. That's the best thing you can do here for this video. And that way you'll be that much more ready for the next exam and learn a little bit more how to do physics exams, and you'll be that much stronger for the next set of exams. But also this is a chance to kind of self-grade yourself. And so as I'm starting here today and starting to grade yours, you'll have a rough idea of how you did, and because of the nature of the exam, I find this best to let you kind of go through and find your mistakes here, and then I'll just grade it and you'll see a score, and I think you'll have a rough idea. And of course there still will be a few questions, and you can ask me those questions and I'll gladly explain why you got a particular score or whatnot. All right, so let's go ahead and begin here. I'll start with the circular motion one here. It says in uniform circular motion and you can see it says it's talking about the acceleration. And you might remember that we talked about an object going in a circle then has to be pushed or has an acceleration towards the center of the circle. And it doesn't really say towards the center of the circle, but the velocity then is in this direction. And so I guess the best choice here would be the second one, B, said the acceleration is perpendicular to the velocity. So remember, an acceleration in the direction it's moving makes it go faster. An acceleration opposite to the direction it's moving makes it go slower. And an acceleration that is perpendicular right there changes direction, and that's what circular means. And uniform means same speed. All right, going on to number 2 here, which actually this could be kind of a tough one here. It says an astronaut visits a planet far from Earth, which is composed of the same material as Earth. Okay, so same density, but has twice the radius. Now, you can see that this is beginning to play out as the universal law of gravity. So I'll just kind of put down the equation for the force between them. And we're not given the mass of the planet or the mass of the person or the radius, but we do know that right here she weighs 900 newtons back on Earth. Okay, so if we called this the mass of the Earth and this the mass of the astronaut, and then this is the radius of planet Earth, all of these numbers come out to be 900. So the question says, how much does she weigh on this distance planet? Now, to do this, we need to say, and I'll just put P for this planet, that it's twice the radius. So it's twice the radius of the Earth. The thing that's not so obvious is the mass of the planet. See, when they said it's the same material, they mean the same density. And since it's a bigger object, it's going to weigh more. And so the question is really along the lines of, well, how much more does it weigh? And maybe I'll grab another piece of paper here, and I'll make cubes instead. But it works for any shape. And in this case, our shape would be a sphere. But I'll draw a picture of a block, and if I made an identical material but twice as big, that means it would have twice the length on the x-axis, but it would also have twice the length on the y-axis. But it would also have twice the depth along the z-axis. So starting with a cube and saying we're going to double its size, That means we have twice the length, twice the width, twice the depth. There's 8. And you can hopefully see in my poorly drawn picture 8 cubes here. And so it's going to be 8 times bigger, or another way of saying it has a mass of 8 times more. I suppose you could just do the formula for volume, 4/3 pi r cubed, and then noting that if you were to double the radius, because it's cubed, you would get a 2 cubed along with your radius cubed. So you'd get 8 radius cubed. And so when you look at the volume of something that has twice the radius, you would say that it has the original volume. So this right here is the original volume, and then 8 times more. And so that's, like I said, probably the hardest part is to recognize that the planet has 8 times the volume. Okay. Now, the other thing to recognize is the mass of the astronaut doesn't change. So if you go to calculate how much does she weigh on this other planet, you would put a G, and you would put the mass of the planet, and that's 8 times the mass of the Earth. And then you would put the mass of the astronaut. And then you would also put the radius of the planet, which, remember, is twice the Earth squared. And when you rearrange things, you will have the same structure as the original weight, and then this extra factor of 8 on the top and an extra factor of 4 on the bottom. And so that is a factor of 2 times this original stuff, which is 900, making 1800. So answer C there would be, or the third answer would be the appropriate one. And so, like I said, that one's pretty involved there. Hope you did that one well. Okay, on to number 3. Question number 3 says that we have a 30 Newton block and it's lifted straight upward. Okay, so 30 Newton block means it's being pulled down by gravity by 30 newtons. And if you pull it straight upward by applying a force of 30, the net force is then 0. And that means the net work, which is force times distance, is 0. And that is equal to the change in kinetic energy. So this is just going to get pulled up with a constant velocity, right? The net force is 0. That would also mean the acceleration is 0. And so whether you do it by acceleration, which is really the topic of last test, or this test where the work is 0, there is no change in kinetic energy. And so if it already had 26, doesn't matter how high you lift it, it's not accelerating, it's just going to keep that same speed, it's still going to have 26. So there's the first 3. Now question 4 is kind of along the same lines, where the work is equal to the change in kinetic energy, and maybe I should say total or net work. But it says a toy car has a kinetic energy of 24. What is the kinetic energy after a frictional force? So we would have a frictional force and times a distance, but remember it's cosine of the angle between, and so the work done is a negative number. And so we've got 0.8 newtons, and it goes for 6 meters. Let's see, 8 times 6 is 48, and then 1 decimal place. Okay, so it's 0.48 joules and negative. It's a decrease in kinetic energy. So it must be 24 minus 4.8. which I guess we'll borrow there and give a 0.2 and then give a 19. So we should be looking at about a 19.2. Looks like answer B there. The next one says we got a 1,000 kilogram car, so we'll put 1,000 kilogram car, traveling north at 12 meters per second. And so I'll call north a positive. It's rear-ended by a 2,000 kilogram truck traveling at 16. And indirectly, they're saying also north because it's rear-ended. And so this is what we would say is the initial momentum. And when we have a collision, and so hopefully you, as you read that, it says if the car and the truck bumpers lock together, so they stick together. So this is what we call a perfectly inelastic collision. What is their speed immediately after? So as far as the final momentum, you could think of it as one big object made out of 3,000 kilograms. And so this right here is 12,000, and this is 32,000, and that has to equal to 3,000 times V. And it looks like if I put these together, what is this? 44,000. And if I divide it by 3,000, I get V, and the thousands cancel off. And then I guess I'll have 44 divided by 3, which I suppose I should get my calculator out here. But 14, 12, and that would be a 2/3. So 14 and 2/3, which is 6666666 repeating. So it looks like it is 14.7. Okay. Number 6 here. A ball with a weight of 3 kilograms. So here's 3 kilograms. Probably would read better. I know that mass and weight we use interchangeably on the surface of the earth. And so it's not wrong, but it would probably read better scientifically if we said a mass. So a ball with a mass of 3 kilograms, because its weight then is mg. And so it's 3 times 9.8. Hangs from the end of a horizontal pole, and the pole is 1.8. What torque does the ball exert? And so the torque is the force, which is this weight, the 3 times 9.8, and then times the perpendicular distance. I think I will grab my calculator for this one. So 3 times 9.8 times 1.8. And how about a 52.9? Is that option available? Oh, yeah, it looks like the last one here. Okay, good. And so there's question 6. Question 7. A child with a mass of 25, so we'll put a mass of 25 kilograms, sits a distance of 1.5 meters from the pivot point on a seesaw. And so that would be pulling it one direction. Where should, and so there'll be an 18 kilogram child here in order to balance it. And so the key to this problem is to recognize a balance due to a torque. And then there's just 2 torques. This one here is rotating it in a counterclockwise direction, and this one here, the 18, is rotating it in a clockwise direction. And so this 25 times g times a distance of 1.5 would be the torque counterclockwise. It must equal to 18 times g and I'll just call it some unknown distance x. That's what we're solving for. And luckily, we don't need to worry about the g's. But as we put in our numbers, 25 times 1.5, and then divide by 18, we're looking at a 2.08, which I guess rounds to 2.1. And so there would be the answer to 7. Here's a great moment of inertia one. It says, 2 flywheels are solid disks. Now, if you remember from this chapter, the rotational inertia, is 1/2 m r squared, where r is the radius of the disk. And so hopefully you took a moment to look in that little table, but 2 flywheels are solid disks, okay? They have the same mass. So in other words, if I was doing a calculation, I'll call this moment of inertia 1 and moment of inertia 2. I would have 1/2 m, and then over here for the second one, I'd have a 1/2 m. And they both each have that same mass. However, even though they have the same mass, one is thinner than the other. And so that means you get the same mass, you make it thinner, and you got to stretch out the radius. And it has, the radius is twice the smaller one. So I'll call r the radius of the smaller one. And so the bigger one has a radius of 2r. And that square is important because as we work out the math here and bring the 4 to the front, you can see that this 1/2 mr squared is the same as the smaller one, the one with the smaller radius. And so the bigger one is 4 times. It says if both wheels are spinning about their axis at the same rate, the larger flywheel is harder to stop by a factor of 2. The larger flywheel is harder to stop by a factor of 4. And so that's it. That's that factor of 4 right there. This is saying that it has more inertia. By how much more? By a factor of 4. 4 times as much rotational inertia. And they don't say inertia exactly, but they do say harder to stop. It'd be harder to get it going, too, because that's what inertia is. So part of this question is knowing what is meant by the word and the meaning of inertia. Here's another one. You probably watched me on the video lectures doing this. Jerry is on a frictionless rotating stool, places a bicycle wheel with its vertical axis. He spins the wheel, and so maybe if we're looking down and here's the wheel, and he spins it in a clockwise direction, viewed from the ceiling looking down, so a top view. If Jerry turns the wheel over, so if you were to, hold a wheel turning this way, and as you turn it over, let's see, so it goes from my finger knuckle to my hand knuckle like that, okay. When you turn it over, it now is going the other direction. Okay. So he spins the wheel in a clockwise direction. If Jerry turns the wheel over, okay, he's got to make up for that angular momentum. So we have something that was going clockwise, now is going counterclockwise. So in other words, we have to have something else going clockwise. And actually clockwise by a lot, because it's got to be clockwise enough to not only have a net clockwise, but then to come off or subtract from this anti-clockwise rotation. And so the person underneath here would start to spin quite quickly in a clockwise direction. And so as I look at my options here, it says rotate clockwise because angular momentum is conserved. And so there's number 9. Okay. Continuing on here to question 10. It says, salt water is slightly denser than fresh water. A 70-ton ship will experience a greater force on, and the answer would be the buoyant force is actually the same, because anything that's floating, and so I'll put something that floats here, and regardless of whether it's floating in fresh or salt water, the water is holding it up, it's supporting it. And so the buoyant force is equal to the weight of the water displaced. And so in this case, we will have to displace 70 tons of water to hold up that ship. And in salt water, it's exactly the same logic, that we need to be able to hold up 70 tons. So it's got to be the same weight of water, whether it's salt or fresh. However, there is something a little different that we should probably mention, and that is the salt water being of greater density, you don't have to displace as much volume in order to get those 70 tons. And so the ship does not sink into the water level. So the water line up on the side of the ship is going to be a little higher in fresh water than in salt water. Or put another way, if you're selling a boat and you're in the ocean, you got your cargo, and you make a transition into fresh water, so you go into port. And in our area, we don't have any freshwater lakes or rivers big enough, but maybe we'll just go up to the Oregon coast there and look at what's the main river that drains up there? Columbia River, and we're taking our load into Portland, and so we've got to come in from the ocean and into the fresh water. And so for 70 tons, our ship's going to kind of lower down a little bit. But if it's a big river, so what, But we do have to be careful it doesn't lower down too much and hit the bottom of a river. All right, well, I hope those multiple choice ones went well for you, and I hope I didn't print this too small for the video screen here. But then we have some free response, and it looks like this one's a conservation of energy. It looks like this is some torques and equilibrium, and this is some angular momentum. And so these two come from our rotation, and these come from our translation in terms of energy. Let me kind of get a pad of paper right here, and I'll just kind of move it up here. But it looks like we kind of load a little toy rifle here. They give us the mass, and they say we're going to fire it straight up. And it's in its loaded position. You compress the spring 0.12 meters. And the sphere is 0.48 below the end of the rifle. So I suppose I'll take this picture. Looks like they're showing the unloaded position, or uncocked position might be a better word, because the ball is in there. But then we push it back and kind of compress the spring. And so that's the 0.12. Whereas the whole thing is 0.48. And that's the part I just read. The spring is compressed 0.12, and the sphere is then 0.48 from the end of the rifle. Once fired, the rubber sphere travels with a speed, and so somewhere up here it has a speed of 5.5 meters per second when it is 3 meters above the end of the rifle. What is the value of the spring constant? So if you remember these problems, they are great ones, and they use conservation of energy. And so that's probably the biggest part of 11A is to recognize that we're going to use this principle, very powerful principle, conservation of energy. Okay? And one of the energies is the mgh or mgy. What is the height of it? Which, if you remember all of our discussions, we have that freedom to pick the height equal to 0 anywhere we want. And why don't I just go ahead and call the starting point the lowest part? That way, when I say the initial energy equals the final energy, I can say that part of my energy, and the only part actually of my energy, is the compressed spring. Because at that point, there's no kinetic energy, so that's why I'm putting a 0 here, but also the height is 0 if that's how I choose to define it. So you got flexibility here, and I have a feeling some of you, won't define it as 0 there, but maybe somewhere else, and that's fine. Now, the other side of the equation, I'll put a 0 for the elastic energy of the spring, because now once we have fired it, the spring goes back to its, uncompressed position, and so there's no what we call elastic energy there. But it is moving, as they say, and it is at some height. But I know all of these except for k, so now I can just put in my numbers, and so I can put a 1/2. And the k is what I don't know, but I do know that I am starting off with the spring compressed 0.12. You can even put a negative if you want, but since you're squaring it, it's kind of irrelevant. And then, like I said, once it fires it, you no longer have any energy from the compressed spring, but you do have a mass, and they told us the mass at 25.5 grams, moving at some speed, which they gave us as 5.5 meters per second. And then we also have some kind of height to it. And of course, that height ties back to what we said earlier. You don't have to call h equal to 0 where I'm going to call it, but you got to call it somewhere. And then you have to measure everything from that height for the rest of the the problem. And so in my case, I called the loaded position 0. So this would go up 0.48 and then another 3 meters. So this must be 3.48 for the height. And so now if I get out my calculator and put in my number there and my number there and move the 2 over and divide by all that, I get a nice number of 174 newtons per meter. Maybe I better check that. So this would be 1/2 times 0.0255 times 5.5 squared, and add to it 0.0255 times 9.8 times 3.48. So that's that whole side of the equation. Bringing that 2 over and dividing by the x squared gives me, 174. Yay! And so there's 11A. And I think I don't want to be too crowded here, but I'll save a little sheet of paper here. I think I can fit 11B on here. Looks like 11B's got 2 parts, but we've got 2 children on one side of the seesaw and a third child on the other side. And so I like to say the torque's making it rotate counterclockwise, and the torque making it clockwise must match if we're going to be balanced. And so that's what they say. We got 3 children. They give us the mass. They give it the position of child A and child C. And each of those are the 2.25 meters. And so the lighter child, the 20 kilogram child, is probably the, smaller one. It's the last time I was on the playground. You often see, my child here and some friend over here, and then their little brother or sister is sitting in front of them and saying, I want to play, I want to play. All right, get on. And they kind of put them up in front there. So that's kind of what I visualize here in this problem. And so we don't know where this lighter child is. But we do know then, and I'll write it this way, that the torque from A and the torque from the lighter child B are each making it go in a counterclockwise rotation. And then the other child is making it rotate in a clockwise direction, child C. So the torque from A would be the mass, which is, 30, times G. So there's our mg, there's a force. And the distance is 2.25 meters. Whereas the torque from the lighter child is its mass, 20 times 9.8, times this unknown position, x. That's what we're looking for here, x. How far from the pivot? That's this question. How far is child MB, or kid MB, from the pivot so that they are in balanced? Okay. Now, the other side of this is the biggest child, 40, times G, times a distance also of 2.25. So once we write all that out, we can see here that that number's known and that number's known. There is a G in every term. So like we saw during the multiple choice, we can either have the G in or not have the G in. Probably should put it in for completeness, and then notice that it cancels off. And so I'll just leave the 20x alone for a moment. But you can see when I bring this over, I'm going to have this 40 times 2.25, and I'm going to be subtracting a 30 times 2.25. And so this is 22.5 there. So then when I divide both sides by 20, I get 1.125 meters for the position of that lighter child. And then also for part B, so I guess I'll do a capital A, because this is problem 11, little b, and this is part A, capital A, because there's also a part B. So 11b, B would be, what is the force on the pivot? So as I look at a free body diagram, there's an upward force, I'll call it UP, pushing up on the pivot, and then there is downward forces from each of the child. And again, to be in balance, the sum of all these forces have to be 0. So we would have a downward force from child A, so I'll put a minus mg, and another downward force from child B, and another downward force from child C, an upward force here from the pivot, and that has to equal 0. So that's the sum of all the forces have to equal 0. So the upward forces really just equal. There's just one upward force, but there's 3 downward forces. So if you take the 3 downward forces and add them together, so we've got a 30 and a 20 and a 40, that makes 90 kilograms. And then times 9.8 is going to give me an upward force of 90 times 9.8. And looks like we are at My apology. I didn't hit 90 all the way. Yeah, so 10 times bigger than that. Seemed small. And so 882 seems much better. 882 newtons. Yay! All right, well, one more. Hopefully, going well for you. And kind of the harder one here. This is our angular momentum stuff. Let's see if I can center it up on the screen here. So, all right. So here is the problem. Like I said, hopefully I printed it big enough you can read it. But here is 11C. And you just did this in the lab, so I'm hoping that helped a lot. That, hey, this is just like the lab. Because you took a disc, and so that's what it says, a 785 gram, 12.5 radius hoop. And so this is the hoop, and I'll go ahead and notice right away that I have a unit conversion challenge, if you will. Because I would really probably like to do things in the base units of kilograms and meters. And so this is neither. So I'll rewrite it as kilograms and meters and point to the top hoop. Now, if you remember, it's not spinning. You held it in your hand in the lab, and then you dropped it onto a spinning disc. And so here's the disc, which is already in kilograms, so no real issue there. It does have a little bigger radius. This is, and by the way, this is not quite matching the numbers in the lab, so you can't just use the numbers from the lab. We're all going to have to go through this math. But it is important to recognize that the mass is in kilograms, so I don't have to convert that, but the radius, I didn't do a good job. I'm trying to cross out that decimal point. It would be 0.162 meters to convert it into meters for the same reason we did that for the hoop. And then, of course, they tell you it's a solid disk. Now, the solid disk is then spinning, and they give you the initial speed. And the key to this is, just like in the lab, and why the lab was called conservation of angular momentum, is that the angular momentum before is equal to the angular momentum after. So if you take the first object and then the initial speed of the first object, and then the second object times the initial speed of the second object, this right here would be the total angular momentum, and since it is conserved, it's going to be the same on the other side. So more on that in a second, but let's do this. It looks like I'm going to need the moment of inertia of the first object, the second object, the initial speed of the first object, and the initial speed of the second object. So why don't I just kind of list those here? Because the first object is a hoop, and then going to that table, it would be 1, which we don't really write, times mr squared. So this would be 0.85 times its radius, 0.125 squared. So grabbing my calculator, 0.785 times 0.125 squared equals, and so we're looking at a 0.0123, and the units would be kilograms and meters squared. So there's the moment of inertia of the hoop. Now the second object, the disk, if we look in that table, has a 1/2 mr squared. So I'll put a 1/2. Its mass, as we were given straight up in kilograms, no really conversion there. But the radius, I'll convert into meters. So this is 0.5 times 1.025 times 0.162 squared. And so we're looking at 0.0134, and again, kilogram meters squared. So almost the same. It looks like the disk is a little bit more. And you can see that the disk has more mass and the disk has a bigger radius, but it also has that factor of 1/2 that the hoop doesn't have. Now, initial speed would be 0 because you're holding it in your hand. That's what it says. And, of course, then they gave this one as 18.2. So this first part of our equation then would be this 0.0123 for the initial, or for the moment of inertia of the first object, the hoop, but times 0 means that that term is going to be 0. Then 0.0134 for the inertia of the second one with a speed of 18.2. So if I just get my calculator at this point, 0.0134 times 18.2, and we're looking at 0.244. And if we want to careful with our units, we'll go kilogram meters squared for the unit of the inertia, and then the speed would be radians per second, and radians is not a unit, it's a clarifier. So if we wanted to put all that, we could, and maybe even should, but it's kind of an intermediate step because we're trying to get the speed, how does it phrase it? It says, what is the rotational speed when they are now spinning together? Because they start to rub, right? Before the ring makes contact with the disc. I suppose I should have put hoop here. Since I put hoop here, but hoop or ring. The ring, hoop, I think we called it ring in lab. And I think your author of your textbooks likes the word ring. No, hoop. And the author of your textbooks likes ring. The ring and the disc rub until they spin together. So as they are spinning together, we on the other side here might call this one object. So we would say that the total rotational inertia is just the two added together, and they would just have one final speed. So this would be 0.0123 for the first one and 0.0134 for the second one. So I can take this number that's already in my calculator and put the 0.0123 and then add it to the 0.0134, close bracket. And let's see, we can then get the 9.50 radians per second. So there is the answer to capital A. And you can see there was quite a bit of work there, and so not a surprise that this is the hardest one on the exam. And the other half of this problem is talking about the kinetic energy. So we want to see how much is lost. So we might say, well, what did you start with? And you might say, well, 0 from the hoop or slash ring because it's not spinning. And then it would be 1/2, I'll call it I number 2 times omega 2 initial squared. And so this is just the spinning part before they come together. And like I said, the ring in your hand has 0 speed, so it's 0 kinetic energy. But the second one's spinning pretty good. And so grabbing my calculator, I can go 1/2 times its inertia, which is this number here, 0.0134. And times its initial speed, and I think we were at, what, 18.2? Yeah, right there. 18.2 squared. And so we're looking at about 2.22 joules of energy initially. Now, you can probably even imagine in your head this rubbing going on. But when you drop it on and there's going to be this rubbing, that's going to make some heat. So we're going to lose some kinetic energy and it's going to go to heat. You probably also hopefully remember it from the lab. You kind of dropped it and you can watch it kind of rub there for a moment until they start moving together. And so when they're moving together, you might think of it now as one object where the rotational inertia is the sum of the two, kind of like we did back here in part A with the momentum, and then it would be the final speed squared. So let me add those two together, 0.0123 and 0.0134. So that's the total there. Let me do the times 1/2. And then let me do times the final speed. So assuming I got A right, I'm going to be 9.5 squared. And it looks like about a 1.16 is the energy after. So not a surprise that it has gone down. Like I said, there's some rubbing, so I would expect it to lose some energy, and so it lost that difference. So 2.22 minus 1.16 would be 1.06. So 1.06 is missing, or we have that much less kinetic energy after they rub, so it must have gone into heat, which as we move forward in this class, we will start using the symbol Q for heat. So I'll just do that right now. So there is the answer to part B. Yay, and there's A, there's B. Okay, I hope that was helpful in a lot of different ways. And hopefully you're able to learn from your mistakes and get a rough idea of how you did. In fact, the multiple choice, I think you probably already know. Okay, take care.